Hello, everyone. This is the week 4 lecture for Applied Statistical Analysis. Today we're going to be going into hypothesis testing. We're just going to introduce it, try to get you an idea of what it means. And then after that, we're going to talk a lot about Z-scores. We're going to talk about them in relation to individuals and to samples. We're going to talk about what that distinction even means and how Z-scores even apply to you as a researcher. So first, hypothesis testing. When it comes to hypothesis testing, what we're trying to decide is there enough evidence in our sample to suggest that there is a relationship or an effect or not? The way we're going to do this is using two competing hypotheses. The first is the null hypothesis. That one essentially says there's no effect. Nothing's happening. The other one is the alternative hypothesis. That one suggests there is an effect. So this idea might seem simple because we can just look at our sample. Does it look like there's a difference between a treatment group and a control group? And if they look different, then doesn't that just say that the effect exists? And it turns out because a sample, there's what's called sampling error. We don't have a sample that's perfectly representative of the population. It isn't so easy. But the idea is we're going to essentially in our minds create a world where there is no effect. We're going to call this here the null world. It's a place where, let's say, our intervention does nothing. It does not help or hurt. It is just null. So if we are living in that world and we took a sample, by chance, our treatment group could be higher or lower than the control group, just due to chance. And that difference is likely going to be small, but it could be a little bit bigger. And so our question becomes, does our world with our sample, with our real data, does that look like this null world or not? If it looks like something that fits in the null world, then maybe the null is actually true. Maybe there really is no effect. However, if our sample doesn't look anything like what the null world would likely produce, then maybe the null isn't true, and we can go with the alternative hypothesis that there is an effect. So I'll let that sink in, because this idea is we're going to keep coming back to it. It's going to get easier as we apply it to certain situations. But the whole idea is we're trying to decide, is there an effect in the population? If we did this intervention to everyone in the population, would there be an effect or not? The way we're going to measure this is with p-values. P-value stands for probability value. It is the probability of observing an effect that large, as large as we saw. So let's say our treatment group scored a mean of 3 and our control was 2, so an effect of 1. So our p-value would tell us the probability of observing an effect that large or larger given the null hypothesis is true. So the idea is we're going into this null world that we created in our minds, and we're saying, how crazy is our result if we really did live in the null world where there wasn't an effect? Is our result really crazy, or does it make a lot of sense? And so the probability value, the p-value, is going to tell us that probability. So if that probability is really small, that tells us this result is really unlikely if we were living in the null world. So maybe we're not living in the null world. Maybe there really is an effect. So all it's trying to do is tell us if an effect exists in the population. Now usually, this is just convention, no real good reason for it. Usually a p-value less than, just note that that's what that symbol means, 0.05 is considered statistically significant. That's usually the line that we've drawn in science. Uh, it is kind of looking like it might change in the future, but right now, that's usually the given. So usually a p-value, so if you got a p-value of 0.01, that's less than zero point 0.5, so we would consider it statistically significant, or in other words, that the effect actually exists. So if we have a really small p-value, we're going to say the null just doesn't make sense with our data, so we're going to reject the null. If we have a big p-value, let's say a p-value of 0.55, that's a lot bigger than 0.05, so we would say it's not significant, and therefore we don't reject the null hypothesis. When it comes to p-values, science, we've relied on them too much. There's this article by Cumming uh, in 2014. It's called The New Statistics, Why and How. It's all about we need to also rely more on effect sizes. So instead of just saying, does it look like an effect exists in the population or not, we should also say, is that effect big or is it small? Is it even meaningful? Using p-values and effect sizes together, we tell this full story of whether or not it looks like there is an effect in the population. And is that effect meaningful? Is it big? Is it big enough for us to even care about? We also need to highlight the fact that effect sizes are uncertain. These are estimates. So there's some uncertainty in them. So even if we get a big effect size, that's just an estimate. We don't know what is really happening in the population. That's just our best guess. Also, if you do find a significant finding, it may not be meaningful or reproducible. It might not be something that's clinically meaningful. It might not be something that really tells us to do anything. So those are things to keep in mind. When we're working with p-values, we're going to look at them and we're going to assess them. But we're also going to focus on effect sizes in this class. We're going to define different effect sizes for different situations as we come to them. All right, so that's it for the brief introduction to hypothesis testing. Please post a question on the discussion board if you have any questions about it. We're going to get into Z-scores. And Z-scores, when I first learned about them, it was really confusing because I didn't understand this point, that there are distributions of single scores. So there's groupings of single scores that we're going to care about. And then there's also distributions of statistics, like means. The difference between these two will be more clear as we talk about it, but it's going to be really important to keep this in the back of your mind as we're going through this. So as we're talking about chapter 4, the very next thing that we're going to talk about, it's all about single scores, so single individuals. Chapter 5, when we get into that a little later, it's going to be talking about distributions of statistics. So a z-score for an individual point. This is the equation for it. It's not too bad. We're going to do a few of these by hand. What this says is this is our value, the individual point. This is the mean, and this is the standard deviation. So what does the z-score even tell us? Why are we using it? Well, if the score is above or below the mean, we're going to know it. If it's above the mean, the z-score is positive. If it's below the mean, the z-score is negative. That tells us that right away. It also tells us how large, in terms of the magnitude, the deviation from the mean is to other data points. And that's because of the standard deviation. So if the z-score is really big, that means this point is really far away compared to other points. If it's really small, that means it's really close to the mean compared to other points. So consider some examples. So we have a mean of 20, our score is 10, our SD is 10. What's our z-score? So here we have our score is the x, so we plug in 10 here. Our mean is 20. So on top we have 10 minus 20, which is negative 10, and an SD of 10. So our z-score is negative 1. So that information tells us a couple things really quickly. One, that it's below the mean, it's a negative value. We can see that here if we see the whole data, but we know that just by looking at the z-score. It's below the mean. And it's not super far below the mean. It's only 1 SD away from the mean. We're going to talk about how crazy that is by using a normal distribution when that fits. But the idea is the z-score tells us a lot of information with just one number. We'll do one more. So we have a score of 5, so 5 here, mean of 5, and an SD of 1. So our z-score is 0. So a z-score of 0 tells us our score is right at the mean. It doesn't deviate from the mean at all. We're right at the average of the whole sample. There's a few others that are included in here. Consider doing those on your own time. Make sure that you understand them. I do tend to ask a question about calculating a z-score somewhere on the exam, so it's good if you can understand how to work with these. So the interpretation, like I was mentioning, if the score is positive, then it's above the mean. If the score is negative, then it's below the mean. If the score is more than plus or minus 1, so if it's more than plus 1 or less than minus 1, lower than minus 1, then the score is considered atypical. So when we scored a z-score of 1, we were right at that border where it's starting to turn atypical. You're kind of far away from the mean. If the score is less than 1 or negative 1, closer to 0, then the score is considered typical. So something to consider is the z tells us more information than just the score. So why is that the case? Well, for one thing, it's because it contains information about the mean and the standard deviation all in one number, which is really cool. You can have one number that communicates all that. In a situation where you have a normal distribution, if your scores have a distribution that looks kind of like this, where most people are really close to the mean, and as you get further away from the mean, there's fewer and fewer people that have that. That's what's called a normal distribution. And when that applies, the z-score also tells us information about how many score below or higher than that individual. When the normal distribution holds, you have what's called the 68, 95, and 99.7 rule. So in the normal distribution, approximately 68% of the observations fall within 1 standard deviation of the mean. So z-scores between -1 and 1, you can see that here, that's 68% of individuals will score right there. If we scoot out just a little bit to -2, so this is 2 standard deviations away from the mean in both directions, that's about 95% of people fall in there. And then if you go 3 standard deviations out, that's about 99.7%. So only 0.3% are out here in this tail and this tail. So just by knowing this, we can figure out how crazy is your score. So if I get a score of -3, we can already say, well, if there's a normal distribution, we can say how many people scored above me and how many people scored below me. If I have a z-score of -3 on an exam, then only 0.15% scored below me. So I did not do very good. But what if I scored a z-score of 2? We already know that 95% are between here. So we just need to add 95% plus what's on this side of that, which if you do the math is just 2.5%. So if I score a z-score of 2 on an exam, then I scored higher than 97.5% of the scores. Hopefully this is making some sense. We're going to go over this in class. Uh, Again, this only applies if you have a normal distribution. If you don't, this does not apply. So consider this example. If scores on an exam have a mean of 70 and SD of 10, we know the distribution is normal. What is the probability of scoring 90 or higher? This is a great question that I could put on an exam. Give it a go, try it out, see if you can solve the example, and we'll go over it in class. Make sure that you understand how to solve this, but try it first on your own. All right, so that's chapter 4, Z-scores. That's about Z-scores for individual points. So we're talking about an individual in a sample. So when we were talking about this right here, if the scores in an exam have a mean of 70 and an SD of 10, what is the probability of scoring 90, so that individual scoring 90 or higher on that exam? But now that we're getting into chapter 5 here, we're going to be talking about the distribution of sample means. So we're not going to talk about individual points anymore. We're not going to ask what's the probability an individual scores this high. We're now going to talk about it in terms of how crazy is a sample mean? Is this a really high sample mean or not? Why do we do this? Because the first time I was introduced to this, I was like, what the heck? Why are we talking about a distribution of sample means? Well, it turns out inferential statistics is all about using the sample to infer population parameters. So we're using a sample to say what a population looks like. But the sample is almost certainly going to differ from the population, at least a little bit, because it's just a random sample. Things happen, they're not perfect. So consider this situation. What if we took 5 different samples, or 10, or 50, or 1,000? Will each sample have the exact same mean? Turns out, no, it's really, really, really unlikely for that to happen. In fact, they're going to differ at least by a little every single time. So we don't want that to be like, oh, that totally throws us off. We want to have a perfect sample. Otherwise, we don't have any information from it. So we actually can use that fact to be able to make an inference about the population. To do so, we're going to use the standard error of the mean. The standard error of the mean, or the SE or SEM, is like a standard deviation, but for a sample mean. The ways it differs from an SD is that it depends really heavily on sample size. So a bigger sample, you have a smaller SEM. Well, this will make sense in a minute why that's the case. It essentially tells us if we were to collect many samples, how much the sample means would vary. If we had a situation, this is totally hypothetical, if we took 50 samples in different places on the university and we calculated a mean for each of those samples, each of them would vary just a little bit. And the standard deviation of those means would actually be the SEM, the standard error of the mean. So when our sample size is bigger, that means our estimate, our guess for what the mean is of the population is going to be better and better as our sample size gets bigger and bigger. So it's going to vary less and less and less and less, and it's going to be closer to what the population mean is. If we have a really small sample size, then we're going to be a lot more over the board. We're going to be further away from the population mean. So this is the equation. It is just a standard deviation divided by the square root of your sample size. So if our sample size is 100 and our SD is 10, we do the square root of 100 is 10, SD 10 divided by 10 is 1, so the SEM would be 1. But the thing is we don't want to take a lot of samples. We don't want to take 50 samples to learn to answer one question. We want to just take one sample and answer our question. So lucky for us, we're going to use statistical theory, or the magic of math is what I like to call it. It's mathemagical. Because we have that, because all these people back in the day gave this a lot of thought, we only need one sample to be able to infer about the population instead of many. We're going to rely on two ideas. The first is the central limit theorem. This one's really intriguing for mathematicians. It actually tells us that the shape, which I'm going to talk about this in a second, what these mean, the shape, the center, and the spread of the distribution of sampling means actually is. So it actually tells us everything about the distribution that we could have gotten if we actually did all the samples. But instead, we can just take one sample, and the central limit theorem will tell us everything we need to know. It tells us that the shape is normal of the sample means distribution. The center is the population mean, and the spread is the SEM. So hopefully this will make more sense in just a minute. But this idea makes it so we don't have to take so many samples. It's really awesome. The other idea is the law of large numbers. As n increases our sample size, as our sample size increases, the sample statistic is better and better at estimating the population parameter. A sample size of 10 is going to give us a decent estimate. A sample size of 100 is going to be a lot better. A sample size of 1,000,000 is going to be way better. A sample size of 1,000,000, we're going to be really, really certain where the population parameter most likely is. With a sample of 10, we're not going to be as certain. There's going to be a lot more noise because our SEM, the standard error of the mean, is going to be bigger. So these two work together to make it so we don't need to collect many samples in order to understand our population. So the Z for a sample mean is going to be the mean of our sample minus the population mean divided by the SEM. This is really important concept. The things that are part of this, the sample mean, the population mean, and the SEM. We'll talk about this more when we get more into the hypothesis testing, especially with t-tests. But this idea is that our sample mean, we can calculate that. The population mean is often unknown. So we don't know this one, and this one we can calculate. So we know these two things, but we don't know this. But with a hypothesis test, what we normally have is a hypothesis of what this is. Often it could be like a mean of 0 or whatever the hypothesis is, and we can test that. So we can plug in whatever number is hypothesized and then plug this in and get a z-score. So we're going to talk about that more later on. Here's some situations to practice with. I'll go over some of these on the board in class. But the idea is you're given a sample size, a mean, a population mean, a standard deviation, and then asked what is the z-score of the mean. What's cool, like I mentioned here with the central limit theorem, is this z-score with the mean, it always is tied to a normal distribution. So we always can get a probability of having a mean greater than or less than. We can always use that because of the central limit theorem. So we're going to be able to use that to actually get our p-values that we talked about earlier. If we were going to use a hypothesis test with a z-score, the question is there evidence of this sample, maybe because of an intervention or whatever, is different than the population or different than a control group? To do this, we're going to rely on a 6-step approach. This is going to be common for every statistical test we use. So when we get into t-tests and ANOVA, regression, all those things, we're going to be using this 6-step approach. So be wise to become familiar with it. Step number 1 is examine variables to assess statistical assumptions. Every time we talk about a statistical test, we're going to talk about the assumptions inherent in that test. So we're always going to want to check, does it look like those assumptions hold? Number 2 is state the null and research hypotheses, both symbolically and verbally. We'll talk about what that means, but we want to be very clear about what the null and research hypotheses are in reference to our study. Third one is define critical regions. Basically is where are we going to reject the null and where are we not going to reject the null. And then after all that, then we actually compute the test statistic. This is a part where we have our data. And in this class, we're going to use Jamovi as our statistical software. We're going to plug that in to Jamovi and have it actually compute the test statistic. It also is going to compute the effect size, and then we're going to describe it. Does that look like a big effect, a small effect, moderate? And then lastly, we're going to interpret the results in the context of our study. We're going to tie it back to our research questions. We're going to say, does it look like the intervention has an effect or not? Is the effect noteworthy? Is it big enough? Or does it look like, yeah, there's an effect, but it's so small it might not even be worthwhile? That is that step. So because Z-scores and t-tests are so similar, we're going to talk about both in the upcoming week. So your job is to read chapter 7 when we get to it next week. Those two, we're going to emphasize t-tests because they're used far more often than the Z-scores. But everything we learn about one is basically going to apply to the other. If you have any questions from what we talked about today, please post them to the discussion board before class starts. This is really a beginning of a lot of complex ideas. Hypothesis testing can be a confusing thing. So please post anything that's coming up. Even if you don't really know how to ask the question, you can say hypothesis testing is still confusing. I don't understand what the null is, or I don't understand what the null world means. Those are great questions. And those are things that we can discuss more in class. And that other classmates who understand it can answer on the discussion board as well.